Bell Labs and so on didn't succeed. EUV was proposed. This is a very different technique. Instead of lenses and so on, they use mirrors. It used to be they say, yeah, next 5 years we'll have it. Well, I believe perhaps in 2010 or 2011, finally EUV will be used. In the meantime, optics has progressed. And so let me tell you the story. So we made a proposal. So this was from Sematech, which is like a cooperative of all the semiconductor companies in the U.S. who will do common research so they can share the intellectual property. So Dr. Karen Brown made this presentation, said, through 180 nanometers, optics is that, even though there are some challenges. But to go beyond, alternatives for below 130 could be non-optical, as I just mentioned. And 100, they felt 100. Gordon Moore said 100 was the barrier. So we made a proposal to them. Multivariable control, simulation, optimization, and signal processing for the microlithographic process. Now, because of time, I had not shown the slides to tell you much about lithography, but let me just tell you in words what it is. What is lithography? You want chips with a certain pattern of lines on it for your circuit design. This pattern is, ones and zeros. You either pass light, you make a mask through which you shine light and focus the beam on your wafer that needs to be processed. Okay. Now, so you design the mask so that you get the desired binary pattern. The light comes on the photoresist on the wafer, and if it's above a certain threshold, it exposes it. Below that threshold, it doesn't expose it. So then they do etching, remove the unexposed portion, and you get your pattern. But the light source is not perfect. There are no lasers that are available at these wavelengths. And the lenses are not perfect. They have aberrations. So if you make a mask with a certain pattern, what will appear on the wafer below is different. So you have to pre-distort the mask so that the combination of the incoherent light and the optical imperfections will somehow combine and give you the desired pattern. It's a nonlinear problem because the pattern is ones and zeros. The mask is a complex electromagnetic device with a different phase and amplitude at each point. So how to design a mask, because light is an analog phenomenon. How to design a mask to get the binary pattern. It's an inverse problem. You know the binary pattern, you want to get a complex number pattern. Well, it's nonlinear, but we found an approximate solution for doing it. And people had such ideas. They were called phase-shifting masks. But the methods for doing it were trial and error. When we were doing this work, we had some engineers come from Intel who were working on this PSM, it was called phase shift mask. They wouldn't tell us very much about what they were doing. But what was true was that it took them about 8 hours to design the mask for a particular pattern that they wanted. Because at every point on the XY plane, they had to put an amplitude and phase. So it was, and moreover, it's nonlinear problem. If you change any dimensions on the mask, you have to redo the whole pattern. Okay. So what we did is found an analytic method of solving this inverse problem approximately, and found some practical ways of implementing the solution. I won't go into all the details. Anyway, the ideas were successful enough that we formed a company. And we were the first people to manufacture a chip with dimension 90 nanometers. We worked with Motorola and Numerical Technologies, the company that we formed, worked with Motorola to get 90 nanometers. And so we broke the barrier for the first time. And then we kept going. And now 32 nanometers is, 45 is widespread use, and 32, at least Intel is probably releasing already, excuse me. What we did is, here, let me read it. the progression, so the title is called Breaking the 0.1 Barrier in Lithography via Signal Processing, from Doctoral Research to Wall Street. So the progression of processing power, as predicted by Moore's law, depends on ever narrowing the line widths in semiconductor lithography. The current predicted resolution limit for optical lithography is 0.1 micron, that's 100 nanometers, using 193 nanometer laser sources and resists that are still under development. That was in 94, 95. Beyond that, there seemed at first to be three options: X-rays, E-beam, and EUV, with mirrors instead of lenses. At present, only the last one has survived, though it is not projected to be production-worthy for another 8 to 10 years. Fortunately, and that was in 94, so now we're in 2009, 10, it's still not production-worthy, though ASML has put out some alpha versions. So then I say, fortunately, it appears that signal processing ideas can allow us to go well beyond the so-called 0.1 barrier, 0.1 micron barrier with existing optical technology. This talk will describe how these ideas emerged from Stanford PhD dissertations, were developed into realistic practical implementation, and ultimately led to the creation and success of the now public company Numerical Technologies. So this talk is directed to a general audience as an illustration of the familiar engineering path from an ill-defined physical problem to an idealized mathematical model, its approximate solution, implementation, and transition to industry. So that's what I call mathematical engineering. It was quite a successful company. The roadshow, when you go around to interest people to buy your stock when it goes public, was done in early 2000 when the market was already beginning to crash. Anyway, we went public with an announced price of 12, but it opened at 22. So it was a successful company and did well. But as Kanwal's point is, after about 3 or 4 years, it was 250 people, it got too difficult for the original management to handle that company. And it's a long story of personalities and so on. Finally, we were forced to sell the company. So management and getting the right people on board and the right personalities is more important sometimes than just having the technology. So what else do I have to say? So I wanted to end with this slide, which came from a New York Times column by Thomas Friedman. He's a well-known columnist for the New York Times. He pointed out at that time, and it's still true, Israel has more companies listed on NASDAQ than half a dozen other countries in Europe and so on. Okay, it's such a country of 4 million people or so. It's remarkable how they do it. So he went to look at these things. He went to universities, and he went to Beersheba University, and the students showed him this project. And this has this title, which, as you can see, even I don't know all the words there, hyperspectral images and so on. Okay, so innovative covariance matrix for point target detection and hyperspectral images. Total jargon to many people. When I told him I was from the New York Times, he declared, this project is going to make the front page. I'm telling you, he's so confident that it will be a success. So Friedman says, well, maybe the cover of Popular Mechanics, but one day it could make the NASDAQ. Yeah. So as Boltzmann said, nothing so practical as a good theory. So, thank you.
Thank you, sir, for your most informative session. I now call upon Professor Shankaran of IEEE to present a memento to Professor Kailath. Thank you, sirs. I now call upon Professor Ramesh Gopal Swamy of IIITB to introduce Professor Mahabala.
Thank you. It's at one stroke pretty easy and very difficult to introduce Professor Mahabala. It's easy because nobody needs an introduction to Professor Mahabala. All of us know Professor Mahabala, so it's pretty easy. I can just call Professor Mahabala here and there will be no loss of information according to Shannon. At the same time, it's very difficult to introduce him in just a minute that I have to introduce him. Professor Mahabala did his PhD in University of Saskatchewan. He has taught there as well as in University of Waterloo and in MIT and a number of other places. We have been fortunate to be associated with him in India in IIT Kanpur and IIT Madras. A lot of us are students for him in IIT Madras and IIT Kanpur. He has been the forefather